catalysis for synthesis using homogeneous catalytic systems. Historically, after the Ziegler-Natta, the metallocene have been discovered. We will see the definition comes in some examples. Then again, we'll keep going with historical discovery. There are the ANSA metallocenes or post-metallocene, and then we'll see some other activations. So, as I said before, we used to say catalyst calling the active site, but we use the same terminology also for the pre-catalyst, which is the catalyst with the chlorine, which is not the active species. So technically it's not correct. Just to make this clear, if you have your catalyst, this is your ligand, you generally start with chlorine, and we also 2-methyl group. So this is not, formally speaking, your catalyst. This is the pre-catalyst. You have to activate this in order to get the real catalyst, which is can be methyl 18 and I can see here. So the free coordination site. Okay. This is your catalyst. This is the pre-catalyst. The chemical you use to activate is used to call co-catalyst or catalyst activate. So, why we have to study the homogeneous catalyst? The Ziegler-Natta has some limitation. Ziegler-Natta catalyst has a limitation. As a multi-site nature, as I've explained before, so it generally produces a wide range of molecular weights. The possibility to modulate the catalyst, yes, you have some possibility, you have seen some donors, but it's not as good as the homogeneous catalyst. So those are called single-site catalysts. So you have one site that works always in the same way. And you cannot produce, for example, block of polymers using the Ziegler-Natta catalyst. Block of polymers, for example, you have in the same chain a block of polyethylene and a block of polypropylene. You cannot do that with Ziegler-Natta. While the rest is same thing. While with the single-site catalyst, you can easily do it, or at least not that easily, but you can do it. They are difficult to study because you have a variety of active sites. So if you want to model catalyst, for example, which active site do you consider? So it's very complicated. And from an industrial point of view, you need patents to produce. Otherwise, you have to pay the fee to someone else. So solution, you have to discover new catalyst. Historically, after the Ziegler-Natta, we have these metallocenes. According to the IUPAC definition, it's just going to read, organometallic coordination compounds in which one atom of a transition metal, such as iron, in this case, titanium, zirconium, hafnium, is bound to and only to the phase of 2-cyclopentadienyl. Cyclopentadienyl is a 5-ring aromatic ligand which lie in parallel planes. So, according to the IUPAC definition, this term should not be used for analogous, which are having different rings, okay, rather than the cyclopentadienyl. So, technically, this is not a metallocene, according to the IUPAC definition. Technically, practically speaking, we call that metallocene. You need to be a bit elastic. So, definitions are always good, IUPAC is always good, but you need to be a bit elastic. These are 2 examples. 2-cyclopentadienyl, and this is called indenyl. So there are 2 indenyl groups. There is a main essential difference between these 2 metallocene. The rings here are not bridged. There is nothing that connects the 2 rings. Here there is something, okay? Can be based on silicon, on carbon. It doesn't really matter. The important thing here is they are bridged. It is very important. Why? If they are not bridged, the 2 rings, they can easily rotate along this bond, okay? And they do rotate. So, if you look at this picture here, there is a C2 axis, So if you rotate in this direction of 180 degrees, you have the same molecule. So it's a C2 symmetric, which can be interchanged in a C2V, which means that there is the same axis of rotational and two planes of symmetry. Okay? Perpendicular to each other. This one can be again interconverted in this one. C2 symmetric. If you bridge the two rings, the interconversion is not possible anymore. So you stick with a C2 symmetric species. In this case, which are the consequences on the polymer you produce? If you don't have the bridge, this coordination site here, it can coordinate the olefins red or C phase according to the configuration of the site. But then it can be interconverted. So it will take another phase. This interconversion has more or less the same rate of the polymerization, which means that your final polymer, if you use propylene as a monomer, it will be attractive. Okay, so this configuration. If you then bridge the two rings, so the interconversion is not possible, it will be always the same phase. Which in the end, you will end up with the same kind of polymer. Which polymers are these? Can you tell me? Correct. Doesn't matter if it's always R or always S, points in the same direction. So this is going to be a string of, if you use the Fisher representation. Correct. Let's see. If you have a bridge, this is the bridge metallocene, and you have a bis einderning, so two rings, fused ring of C6 and C5. This is your chain, okay, which goes in this direction because here there is the ligand, okay. It will point in that direction. The methyl group points in the opposite direction, similarly to the Ziegler-Natta catalyst, and will take always the same phase. You insert the monomer, so this one becomes free, where the olefin can be coordinated, and it will take again the same phase. The chain will point in this direction, and the methyl group will point in the opposite direction. Similarly, if you have the enantiomer, it will take always the same phase. In the end, you end up producing the same kind of polymer, acetate polychrome. Yes?
A question. When they're not bridged and they manage to rotate, the polymer, if that is going to create, it's random or?
It's random.
It's random. Because here is not.
Sorry?
Because here is not that random, it follows the pattern.
Which kind of polymer?
Yeah. I think that's coincidence, I think it's actually not. And it's still atactic. It's not semi-atactic or...
So if this would be syntactic, it's going to be all R.
No, yes, but maybe.
If you think it's a stereo error, you have 3 stereo error at least in 6 insertions. I call that atactic or not zero regular.
And also and that's just a small excerpt of the.
Yeah, it's something like 1, 2, 3, 4, 5, 6, 7, 8, 9. You have 9 insertions. In these 9 insertions, you have, let's say, at least 3 mistakes.
Oh yeah, but could be even more random, like MM, RR, MR, MO. It could rotate.
It could do that, yeah. It's just an example, but in the chain you will have a random distribution. Okay? If you then change the ligand, so you have a cyclopentadienyl, this is called fluorenyl group. So you have 3 fused rings, 2 benzene and 1 cyclopentadienyl. So here there is a sigma mirror, which means it's a plane of symmetry, which goes in this direction. What happens to your final structure? again, we have to look at the chain. If this is your monomer, this is your chain. The chain will point in this direction, okay? Because here there is a ligand. So it will take the ray phase for the monomer. After insertion, the chain will go up. But in this case, will be pointed in the opposite direction. Sorry, in the same direction. Because there is the ligand here. So it will point here, which means that the methylene will point in the opposite direction. So it will take the C phase. What happens when you take the R phase, C phase, R phase, C phase? It's going to be synetap. So RS, 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 or a string of R. Is it clear? So there is a kind of relationship between symmetry, C2 symmetry, isostatic polypropylene, CS symmetry, syntactic polypropylene. Okay. What kind of stereo defect we can see? You have a R, then you have double M and R. We have seen this before. It looks like a side control stereo defect. Okay, so there is a mistake here. This is supposed to be down. Then the side control is up. You can also get this. What is this? It looks like again a chain and control, but in this case it's not. What can happen here? Let's go step by step. So, for this kind of catalyst, it's a metallocene catalyst again. Start from top left. So your configuration in the chain is S. Okay. Then you have the olefin coordinated. It can insert and it goes in up because it produces indutactic. Okay. What can happen? The chain here, it doesn't like to stay there. Okay, this happens especially if there are big groups. So the chain is not happy there and it wants to go in the other side. So this chain goes here. It keeps the R configuration. Then the propy can coordinate and get inserted. So you have an RR configuration. Okay. So this process here called cytopolymerization, it has been found for metallocene. It can happen. It happens especially when you have big groups over your ligand. So the chain, it doesn't like to stay in one place and it goes in the other side. Okay?
So epimerization is basically the movement of the chain.
The chain. That's it. What happens if we break the symmetry? So not C2, not CS, but C1. So there is no plane of symmetry, no axis of symmetry, there is nothing. So one side will be again stereoselective and regioselective. So it will take always the same phase for the protein. But the other side is not regioselective. Sorry, it's only regioselective, but it's not stereoselective, which means that the chain doesn't really know where to go. So it cannot give stereoselectivity to the monomer. If only one side would be stereoselective, means that this one is regular, this one is regular, this one is regular, this one is regular, alternated, but this one, these are not. So once will be R, once will be S. So we call this hemiisotactic, which means that something like 70% of the structure is stereoselective or stereoregular, I should say. The remaining 30% is not. Okay? So there is a kind of stereoselectivity, but it's not fully stereoselective. After metallocene, now we are going to see some what they are called ansa-metallocene. So homogeneous catalysts, which have been developed just after the metallocene. And the first step to do say, okay, do I necessarily have to have a cyclopentadiene? Can I change with something else? For example, nitrogen. Yes, you can. And these are called constrained geometry catalysts, which means that this angle it gets smaller and smaller according to which you have here. What do you have here? So if you, this is a constrained geometry catalyst. So if you use nitrogen, this angle here is small, which have the implications. You have a lot of space here, okay? So your olefin can be bigger. So it can incorporate a higher alpha olefin, Xe, 4-methyl-1-pentene, they are very big monomer, okay? So it's difficult to give zero regularity in that case, or at least most of the catalysts do not polymerize very large olefins because they don't sit, they cannot coordinate the catalyst because there is too much space from the ligand. But for this constrained geometry catalyst, there is a lot of space here. So these catalysts are generally used when you want to incorporate larger olefins, okay? They are quite, if you use propylene or ethylene, they are quite active because same reason. It's very big, so the olefin can easily, or the propylene can easily coordinate the catalyst here. So the steric repulsion from the ligand is much less compared to this base here, for example. Okay. And that's an important thing. Berger can tell you this. These complexes here are difficult to synthesize. You have to have quite a lot of steps, especially if you are going to modify all the possible positions. It becomes very complicated, low yield. These catalysts are much easier to synthesize. It's important, well, if you produce tons, in terms of costs, the cost of this one is much cheaper compared to this one. So in the price of the final product, it is important which kind of catalyst you use. So if you go to industrial scale, this is extremely important factor, okay? The cost of the catalyst. And also for this reason, we went with this kind of catalyst. They are called ANSA metallocene, so it's the normal step after the metallocene or constrained geometry catalyst. Do I necessarily have to have the cyclopentadiene? Not necessary. In this case, this is one of the ANSA metallocenes. This one has been discovered in the late 90s, early 2000. It's a phenoxyimine. This is a mistake here. It should be a double bond. My apologies. You can see it here. So there is an oxygen bound to metal, and this nitrogen coordinates the metal. Okay, this is a coordination. And you have a bis because two of these bound metal. Phenoxyimine catalyst. Now, what is particular of this catalyst? The synthesis is relatively easy, and the geometry is the same as the Ziegler-Natta. So it's a distorted octahedral geometry. But what is important here, you can modulate this catalyst a lot. So you can place something here, something here, something here. I have limited these three because there is a particular reason, but you can also modify here, here, and here. So you can modulate a lot the catalyst, and it's not particularly difficult. You can actually modulate also the metal, that they call hafnium. Let's see a bit more in detail. I like this catalyst because it can be easily produced and studied. What is the function of R1 here? So the bigger is the alkyl group in this region here. Sometimes we found a trend between the bulkiness of this group and the catalyst activity. The bigger is the group, the higher is the catalyst activity. It sounds counterintuitive because you increase the steric demanding. So the olefin, if it's more, should be more difficult to coordinate the metal. We will see later this one. So according to how big is this space, you have a more or less steric demand. This group here is very close to the active site. So it points really toward the active site. R2, what is the function of R2? it has been reported that this group here, it's quite far from the coordination sites, okay? So technically it should not matter a lot if it's not for the electron of the metal. So what people have done is to functionalize this group here and support over any support, something like silica, for example. So you can make this homogeneous catalyst that works like an heterogeneous catalyst without affecting too much the catalyst activity, or not affecting the two, because it's quite far from the coordination sites.
Can I just
Yes, sure.
say something? We discussed exactly that last week. Taking a homogeneous catalyst and making it heterogeneous with all the advantages.
And that's the reason why I have not included why we should support, because I know you've done. So
Just
I
to
didn't
remind,
want to-
just to remind everyone.
Yeah. Third group, R3. This is a C2 symmetric catalyst. Okay? There is a C2 axis of rotation, so you can rotate over 180 degrees and you can obtain the same catalyst. We have said before, C2 symmetric catalysts generally give isotactic polypropylene if you use both. In this case, this one doesn't. It gives syntactic. It's an exception. Why? It's a very peculiar catalyst. Let's start from here. This is your chain, and this is your propylene, okay? Now, let's imagine you have the C coordination of the propylene, and you have the delta form, okay? So you insert your monomer. Let me see. Here, sorry. You insert your monomer. Then what a catalyst does, after each insertion, it changes the form. So the delta form interconverting the lambda form interconverting the delta and vice versa after each insertion. Which means that once it will take the C phase, once will take the R phase, the ref phase, after each insertion. It's a peculiar behavior of the catalyst. So you do not expect a C2 symmetric catalyst that gives syntactic polyolefins. And this is the reason why. Now, where comes the R3 group here? What's this function? If you increase the bulkiness of this group, the interconversion between the delta and the lambda is a bit more complicated, because it is expected that the interconversion it's a mechanism where you have to change the configuration. So this group here, if it's quite big, is going to collide with the other one, these two. Okay. So if you increase the bulkiness, you cannot have any more these flip in the configuration. Another important factor of this catalyst, I like this catalyst and I'm using it a lot. If you change the alkyl group over the nitrogen, and you have in particular fluorines here, it is found that this catalyst can produce extremely high molecular weight, which is something not easy to achieve, very difficult to achieve. Why? I think you have done the chain termination mechanisms, and you have seen the alpha, beta, hydrogen elimination, okay? I think I've done this. So this is the beta hydrogen over the chain, and it has been studied for this catalyst that this hydrogen, which is the responsible for the chain termination, it is stabilized by these fluorines in ortho. Okay. So as I mentioned before, let's see. Okay, you cannot see the Bluetooth. This hydrogen in beta interacts. So this 2.2, 2.3 angstrom is quite close. So there can be a influence of the orthofluorine that stabilizes the hydrogen. And this hydrogen is quite close to the titanium. Okay, so generally what happens, it may happen, is the beta hydrogen elimination. So the hydrogen is taken from the metal and the chain is released with the vinyl group in the end. In this case, this hydrogen is stabilized by this fluorine. So the beta hydrogen elimination is suppressed.
Mm.
And that's the reason why you can achieve very high molecular weights. Okay. There is a debate here. Some people say that this fluoro effect actually does not really exist. It's more the bulkiness of this group that destabilizes the beta hydrogen elimination. Or another group says that this fluorine actually interacts with metal rather than the hydrogen in beta. And that's why it does not terminate the chain. It doesn't really matter. What is important here is that with this kind of catalyst you can achieve extremely high molecular weights. Okay? Which is again not, it's very difficult to achieve with single cell catalysts. These are other examples of post-metallocene catalysts. We used to call very simplistic way O catalyst, just for simplicity. Of course, you are missing a lot of information. Or ON and O, it's just a way to call them. It's very it's not really, I can say, formal, but it's handy. Okay? So these are examples, just to give you an idea, a flavor of how much you can modify this catalyst. So in terms of groups that you can place, in terms of ligand, also the catalyst can be any kind of catalyst, not only group 4, but can be also overall the D block, which is something which you cannot really achieve with Ziegler-Natta catalyst. Okay. Now this is a different example of post-metallocene or answer-metallocene catalyst. It's based on hafnium. This one is the pyridylamino hafnium 4. Why this one is important? It has been discovered. This is the first catalyst discovered with high throughput technologies. So what are these high throughput technologies? They are machines, robotic machines that can mix chemicals, test the catalytic activity in a very large number in a reduced time. So you can produce something like hundreds of compounds in one day and test hundreds of polymerization in a single day. And it's extremely difficult to find a new catalyst class. It's very difficult. In 60 years, there are quite a lot of catalysts discovered, but not many. Okay. Using these technologies, in only 2 years, this catalyst went to production. Generally, it takes 20 years. Okay. So it's a kind of trial and error. So you just test, mix stuff, test, and see what happens, and end up with this catalyst. So this catalyst produce isotactic polypropylene. There is a serogenic point here. Where do we expect the first insertion here? What we have seen? This is the pre-catalyst. Okay. Where do we expect the first insertion? Just guess. You have two methods here, okay? Generally what happens is you extract one to produce a cationic species, and then the olefin coordinates, and you have insertion. So you expect the first insertion or here, correct? Here is your first insertion. So you extract the first methyl group, you produce a cationic species, your olefin coordinates. This is also a carbon metal bond. Technically, the olefin is going to insert in a metal carbon bond. So I can insert here, but also here. What people have found for this catalyst is that only the first insertions occurs here. And then it goes in the normal way that we know. Generally, when you see these kind of things, you see an induction period in your catalyst. So generally what you do is you prepare your reactor with all the chemicals, then you inject your catalyst, and you see a consumption of your monomer, ethylene or propylene. if there is an induction time, means that in the beginning nothing happened, so there is no consumption of your monomer, and suddenly it starts consuming your monomer. According to the group here R, you can have, okay, this is just an example, but you can have this kind of induction time. So the polymerization itself does not occur yet. Something first has to happen, which could be this, for example. Okay, it's a peculiar case. We are just seeing one of these. Here we are not looking at the catalyst itself. We are looking at the different kind of way to produce polymers. So there are no new catalysts here. That you use two catalysts, catalyst 1 and catalyst 2. What is interesting here is the use of a third component, which is not a catalyst, is a chain transfer agent. So let's say a bit more in detail. You use catalyst 1, which produces an hard polymer, for example polyethylene, and catalyst 2, which does not incorporate the ethylene, but produces a soft polymer. For example, if you have hexene in solution, incorporate hexene. Then you use a chain transfer agent, which is this one here, which can take this drawing chain here and give to this catalyst. Okay. So this catalyst generally doesn't like polyethylene. It takes the chain, but it does not keep producing polyethylene. It stops producing polyethylene and produce only the soft chain, or polyhexene, for example. The same here. The chain shuttling agent takes the soft chain, gives to catalyst 1, which does not like polyhexene, for example, to produce polyhexene, but likes to produce polyethylene, and produce the hard block. So this is a process discovered by Dow chemicals, and it's a very peculiar way to produce hard, soft copolymers. It's relatively old, quite old, 10 years maybe, 10 years old. And a bit of catalyst activation. So, as I mentioned before, we have the pre-catalyst. You have to activate the catalyst, the pre-catalyst, in order to get the real catalyst. So, this is a classic mechanism when you produce the active site. So, you have the pre-catalyst, and you use your co-catalyst. It generally contains a methyl group or an active group. So it takes one chlorine and gives a methyl group. Then the same co-catalyst or another co-catalyst can extract the chlorine, producing the active species. These active species can then polymerize, okay? We tend to write this species here like this, because it's ended. But don't forget, you never have a cationic species just like that. You always have the counter anion somewhere. Okay? You always have like something like that. That's what we are going to look at now. The co-catalyst, which is generally the counter anion, because it has taken a chlorine, it goes close to the metal. Different cationic charges will go close together. You can have different configurations. A configuration when your chlorine can coordinate a bit your active site, or the co-catalyst with an anion, the electron-rich portion of the co-catalyst, we will see later, can coordinate the metal, or another kind of configuration where you have your solvent that coordinates the metal and the co-catalyst is somewhere there, or at the back of the catalyst. So here is very free, and co-catalyst is at the back. These are possible configurations. Your catalyst activity depends very much on which kind of configuration you have. Just to give an idea, if your co-catalyst, we used to say it's very sticky, so it coordinates quite strongly your metal, your olefin cannot coordinate your catalyst. So you do not have, or you have a very low rate of polymerization. If you have this kind of configuration, your co-catalyst is quite far from the active site. So there is space for the ethylene to come. And I always say the co-catalyst is almost as important as your catalyst. If you have something like this, you may have you have produced the most active catalyst, but if you do not activate properly with the right catalyst activator, you may have no catalyst activity, because you can form something like this. So you can even produce the active species, but it's not active enough because it's stopped the catalyst activity by the co-catalyst. So the ideal situation is something like this, where there is space for the olefin to come and insert. This is another remarkable example. It's the discovery of one of the most used co-catalysts. Let's take an example. This is a interleaved metallocene. And if you activate with aluminum trimethyl, and this is history, they used to have very pure catalyst activity. Then one day they have done an experiment, same experiment, but the reactor was dirty of water. Water is a poison for these catalysts. These are extremely sensitive to air and water. If there is a bit of water, you break down the catalyst structure and you have no catalyst activity. So they end up with a very high catalyst activity. There is something wrong, something different, strange. What happened here in this case, and this is really happened, is the formation in situ of one of the most famous co-catalysts, the MAO, the methyl aluminum oxide. This co-catalyst is formed by the controlled hydrolysis of trimethyl aluminum with water. And you have this kind of structure here, with methyl group on the side of the structure, with N around 420 units. Now, the real structure is not clear, which one is it. So after over 30 years, people have studied this MAO, but no one knows the real structure. Probably because it's a mix of these structures. This structure is used to say it's a cage structure co-catalyst. So you have rings of 4 centers and 6 centers with these methyl groups at the edges. So we believe that these methyl groups are the one that are given to the metal, and aluminium extract the chlorine. Bear in mind, this reaction, you really don't want that to happen. It's extremely dangerous. Just to give you an idea, once I had a very small vial or 8 milliliter vial, it was empty. It was dirty of this chemical. It was only dirty, that big. I opened it to clean. I just opened the cup, and a flame big like this came out from the vial. It was that big. It reacts extremely violent with the oxygen and water which is in the air, and it was only dirty. So just to give you an idea, if you ever try to do this, don't do it. Just buy the material. But if you have to do, bear in mind this. It's extremely dangerous. All aluminum alkyls are very, very dangerous. Okay? So why it's important? Why it works quite well? If this is your co-catalyst, it's huge. It's very big. It's probably bigger than the catalyst. So you form this kind of configuration here. So it cannot really coordinate the metal because it's too big. Okay, so it cannot sit here. It's very difficult, and it will sit somewhere else. Okay, so your ethylene, it's free ethylene, probably whatever is your monomer, it's free to go to the monomer, to the active site, and you can have the polymerization. There is a problem with MAO. MAO contains the starting material, the trimethyl aluminum in equilibrium with the polymeric form. This one can generate different cell direction. One of these is the formation of these dimethyl bridge aluminum compounds. which can stop the polymerization. It depends on the catalyst. Sometimes you can have this form here, which is called dormant site, and the catalyst stop working. It's not always the case, but it can happen. They are not active because they do not produce a polymer, but technically they can be activated. For example, in Ziegler-Natta, they can use also hydrogen, which is a bit smaller. You can push away this, terminate the chain, and start a new one. It can do something else. If this is your polymeric chain, you can have a similar structure, similar species, but then the aluminium takes your polymeric chain and gives a metal group. So it cuts the chain, the growing chain. It reduces your molecular weight. And if you want to produce very high molecular weights, this is something which is detrimental for your process. So you cannot avoid. You have MAO in equilibrium with your trimetal aluminum in equilibrium with your polymeric species. What you can do, this is another example of catalyst deactivation by the trimetal aluminum. So this is the catalyst we were seeing before, the bisphenoximine. It has been studied for this catalyst. The aluminum trimetal can actually take the ligand from the catalyst and reduce your concentration of catalyst in equilibrium. So basically, break down the catalyst structure and reduces the productivity. Okay? It depends on the catalyst structure. What you can do, if you want to use MAO, you can produce solid MAO. Now, one step back. The MAO is sold as toluene solution. So you have a toluene containing about 10% of MAO. So most of it is toluene, solvent, and you have this 10% of MAO. What you can do, the trimetal aluminum is generally in solution. So what you can do is to remove the solvent, and you have this dried MAO, solid MAO. Then you can use these to activate the catalyst. Of course, if you place back in solution, it will release again trimetal aluminum. It depends what you're doing. Depends the catalyst, depends what you're doing. If you want to use the solid MAO as a support, you can do that. If you use gas phase, you can do that. But if you are in solution, no one can stop the solid MAO to release again trimetal aluminum. What you can do is to chemically remove as well the trimetal aluminum by reaction with the phenol. This is the bis-2,6-terbutyl phenol. This is a poison for the catalyst. Phenols are poison for catalyst. Because of these big groups at the site, if your catalyst structure is quite big, you do not have interaction between the phenol and the catalyst. For example, we have seen before this kind of catalyst here. This catalyst wants to react with the phenol group here. But because of these terbutyl groups here and here, it cannot manage to see the titanium. So the oxygen wants to react with the titanium, but because of the terbutyl groups, it cannot. So what you can do is to use this compound, to react with trimetal aluminum and give this species. If you use an excess of, this is called BHT, if you use an excess of this species here, you can produce this kind of species here. So you chemically remove, you scavenge the trimetal aluminum from the solution. This is a process which is done quite often to scavenge the trimetal aluminum. So you avoid chain cutting, chain termination, and catalyst deactivation. Okay. You don't necessarily have to use MAO. You can use also different kind of activators. Boranes are an examples. On top here there is the pentafluorochlorate.
Trisperfluorophenylborane.
This one is yes, it can activate your catalyst, but it's not as good as MAO and these two gentlemen here. What's the difference? This is a much stronger catalyst activator. So you have your anion, which is quite bulky, stays there, and this carbon here wants to get the methyl group or the chlorine from the catalyst, and you have the catalyst activation. Something similar can happen here. So you have this tetrakis pentafluoroborate, that one, and this species here, which is cationic, tend to protonate in methyl group. So you release the methane and you form the active site. We have seen an example before of this catalyst. Generally, hafnium metal can form the dimethyl bridge species with trimethyl aluminum. So if you use hafnium based catalyst, you don't want to activate this when there is trimethyl aluminum around, because it will stop your polymerization. So this catalyst is generally activated with boranes rather than MAO. Metallocines and also these kind of catalysts are generally activated with MAO. Big difference. We don't know the structure of the MAO, but we know the structure of this co-catalyst. So if you want to modulate, use computational methods to study your catalytic systems, and you want to include also the effect of the co-catalyst, it's difficult to model something that you don't know. So some people, what they do is to use these boranes, because the structure is well known, and they can predict or modulate the stereoselectivity and how the catalyst works using these boranes. So main difference between MAO and boranes: boranes well-known structure, MAO catalyst unknown structure. Okay. Differences in the ion pair. So some can produce very sick ion pair. For example, this one is less sterene demanding compared to this one. So the fluorine, one of the fluorine can actually easily coordinate the metal and can stop your polymerization. MAO is very big, so it's more difficult for the MAO to coordinate the catalyst. Of course, it depends. Always depends on your catalyst and co-catalyst.